Okay, all right. So we can start. And so the assignment will look like this. I will show you the maths assignment. It's going to be released in a few days. So I'm very sorry for the delay. I'm going to share my screen, and it is this one. Okay, so it's inequalities. All right, so and it's due for the 14th of April. So we talk about inequalities, like solving an inequality like this. All right. Hard inequalities and quadratic inequalities, so stuff like this. So in most cases, you can work them out. You can work them out logically. I won't touch inequalities today, but mostly I'm going to talk about physics again. All right, so today's topic, you see problem 6 is inequalities. I'm going to talk about inequalities a little bit, but before the assignment is released, I don't want to spoil it for you. Okay, so problem 1. You see a marble is pushed up the slope by a compressed spring. So we compress the spring, we release. It's like a toy. You can imagine it. We'll do this problem. A toy gun shoots a 20-gram ball when a spring decompresses. So the spring is compressed and it releases a toy ball. Okay, so a marble is pushed up the slope by a compressed spring. The spring was compressed by 2 centimeters and the spring constant is 200 newtons per meter. How high up the slope will the marble of mass 10 grams roll? How far will it travel? Okay, well, since we're doing the conservation of energy, we need to inspect what type of energy do we have at the start and what type of energy we have at the end. Okay. So what type of energy do we have at the beginning of the process? Kinetic. Yeah, when it's released, it's kinetic. But before it's released, what's it going to be? Be a bit more specific. What type of energy? Elastic potential energy. Yes. So at the start, we have elastic potential energy stored in the spring. And at the end, the ball is here. It's reached the maximum height and it wants to roll down. So at the end, it only has gravitational potential energy. So we can, of course, in the middle, it has kinetic energy plus gravitational potential energy. But we don't care about the middle. We only look at the start and the end. So we have elastic potential energy going into gravitational potential energy. That's what we're going to do. The elastic potential energy is 1/2 kx squared, where x is the extension, and that's equal to mgh. And from here, we can work out the height at which it will roll. So h is kx squared divided by 2mg. And we can substitute that. So the spring constant is 200. 200 times x. It was compressed by 2 centimeters, so 0.02 squared over 2 times mass. Mass is 0.01 kilogram, and g is 10 as usual. So 200 times 0.02 squared divided by 2 divided by 0.01 divided by 10. So it's 0.4 meters. So the ball will climb 0.4 meters. meters, the height. How far will I travel? How far along the slope? Let's call it L. How would you work out L if you know height? Height is 0.4 meters. L is, yeah, trigonometry, of course. Oh, well, length of the bottom, but you still need to use trigonometry. The angle is 30 degrees. So that's 30 degrees. So you can work out. So can you work out, please, L? Height reached. Zero 0.8, yes. 0.8 meters, so 80 centimeters. 80 centimeters and 40 centimeters. Okay. So L is H divided by sine 30. And sine 30 is a half, so H divided by 0.5, which is 0.8 meters. Perfect. So we've answered the question. The ball will roll. And interestingly, we're not taking into account the shape of the slope to answer the first question. Like even if the slope was like this, it would reach a height of 40 centimeters, regardless of the shape of the slope. And even if the slope was like this, if you needed first to go down, if it was pushed down, and then it will travel, it will speed up first, then it will start to slow down, and it would reach 40 centimeters above the original height. Of course, if you ignore friction. This is a very cool fact about conservation of energy, because if you have a simple slope, a straight slope, you can use suvat. Here, there's no way you can use suvat, but still conservation of energy works. Now, did anyone notice that I cheated a little bit? Did anyone notice that I cheated a little bit? Okay. What's your thought? Where did I cheat? I cheated with defining what H is. So I said H is 0.4, but what is H? What was the cheating that I've done? Yeah. No frame of reference. Well, sort of. I forgot about these 2 centimeters. Where are they? Do I include them at all? So because the ball started here, because the spring was compressed and then released. So I have to measure from the bottom, and it's 0.4 from the bottom when it was compressed, or was it 0.4 from when it was the moment it was released? Well, it's 0.4 from the bottom. So if you take from the distance from where it went left the spring, then you would have to use, it would be 0.39 meters, because 2 centimeters. But generally speaking, you can usually ignore this the stretching of the spring because it's much smaller than the length of the travel. Okay, so if you were considering, I don't know, you're considering how far can a gun shoot, you don't usually consider the length of the barrel, right? If the gun shoots at 3 kilometers, well, is it 3 kilometers plus meter or -1 meter? Doesn't really matter, right? So you can usually ignore, unless there's special circumstances, you can ignore the length of the spring, of the change in length of the spring at the beginning. I hope that makes sense. Okay, now in the previous problem, what would the answer be if there's a friction force? Interesting. So now we shoot off, the ball travels off, but now there's a friction force on the way that slows it down, so it converts kinetic energy to thermal. So work is done, so some kinetic energy is lost. So at the start, we have elastic potential energy, and at the end, we have gravitational potential energy plus the work done, which is heat, it's thermal, which has converted into thermal. So that's what we need to work out. And the work done is force times distance. Well, obviously it's negative. It's force is 0.02 and the distance is L. So work done is force times distance times L. That's important. That's the first thing. Then gain in gravitational potential energy is mgh, which we don't know. But we know that this is h, and this is L, and this is theta. So we know that L is h over sine theta. So we can plug that in to here. Or, yeah, it doesn't really matter which one we use. I propose we use h as in L sine theta. So we can use this as mgl sine theta. And L is the unknown value we're looking for. Okay, so we have elastic potential energy is used up to increase the gravitational potential energy, plus do some work. Does that make sense? The elastic potential energy that we have at the start is used to increase the gravitational energy and also do some work on the way. Yeah, makes sense, Mark? Okay. So elastic potential energy is 1/2 kx squared equals mgl sine theta. We worked it out. Plus the work done, which is force times L. So we can work out L from here. 1/2 kx squared equals L, open bracket, mg sine theta plus F. So L is equal to kx squared divided by 2 multiplied by mg sine theta plus F. Okay, let's see what that gives us. So K is 200 times 0.02 squared divided by 2 times 0.01 times 10 times 0.5, because it's sine 30, 0.5 plus force is 0.02. And that, is it? Oh yeah, 0.02 newtons. So 200 times 0.02 squared divided by 2 divided by 5, 0.05 plus 0.02, which is 0.5, 0.57 meters, 57 centimeters. 57 centimeters. Then it makes perfect sense, right? It will, because if there's friction, it will only go up by 57 centimeters. And the height would be L times sine theta, which should be 57 times 0.5, which is going to be 20 times 0.5, 0.29, 29 centimeters. 29 centimeters. It will only go up 29 centimeters rather than 40 centimeters, which also makes perfect sense. Now a question will be, how fast will it be traveling when it hits the spring? How far, how fast will it travel when it hits the spring? How can we answer this question? Please use your mic. Someone? How would you answer this question?
Is gravitational potential energy equal to kinetic energy? So when it goes back down, it'll be the same speed as going up.
That would be true if there was no friction.
Or because since it's going down, you also have to take into account gravity.
Gravity, so at the top you have gravitational energy. So at the start, you have gravitational potential energy, yeah? At the end, what do you have? Kinetic energy plus heat. You've lost some of the energy on the way down because you lost some of the energy on the way up. You will also lose some of the energy on the way down. Okay, does that make sense? I just got a message that maths is ready to be published, so I won't publish it. No, sorry, I'll need to read it through again, but I won't publish it tomorrow. Okay, so gravitational potential energy at the start is kinetic energy plus heat, or the work. Gravitational potential energy is mgh h1, let's call it mgh1, equals 1/2 mv squared plus, we know the distance traveled, it's the force of friction times L. You see, I'm ignoring the sign because I know it has to be positive, right? Because kinetic energy is going to be less than gravitational. So work has to be positive here. Because if work is negative, then kinetic energy would be bigger than gravitational potential, which doesn't make any sense. So in physics, very often, you can ignore the signs and just use your common sense. Because you know that this has to be positive, this has to be negative. Okay, and now, what do I do? Well, let's multiply everything by 2 and then divide everything by m and then find the square root of everything. So multiply everything by 2, so 2 mgh1 equals mv squared plus F friction times L. Then we divide by m, so 2ghi1 equals v squared plus F friction times L divided by m. And then v is equal to square root of 2gh1 minus F friction times L divided by m. And you can see the speed depends on the height minus the friction force, minus the work. So we can do 2 times 0.57. Oh no, 2 times 10 times 0.29, because that's the height, minus F of friction 0.02 times L is 0.57, because that's the distance traveled, divided by the mass, which is 0.01. And we plug that in, we get square root of 20 times 0.29 minus fraction 0.02 times 0.57 divided by 0.01. And it's going to be 2.2 meters per second. Interesting. Well, we don't know how fast it left. We don't know how fast it left, so let's so return velocity. So what is the launch velocity? Let's calculate the launch velocity as well. Just so 1/2 kx squared. So that's the potential energy stored in the spring, and that's equal to 1/2 mv squared. So 1/2 cancels, and we have velocity. Well, let's call it u. U squared is kx squared over m. So u is equal to square root of k over m x. Ooh, interesting. The value is interesting. It says 200 divided by m, which is 0.01, times x 0.02. So it's going to be 2.8 meters per second. So as you can see, the return velocity is not the same as the launch velocity. So it launches at 2.8 meters per second, and it comes back down at 2.2 meters per second because it's lost some of the energy is dissipated as heat. I don't think you multiply it by 2. Oh yes, I haven't. So 2. I'll need to recalculate that. Square root of 20 times 0.29 minus 0 minus 4 times 0.57. 1.87. Okay, 1.9. 1.9. And that is 1.9. Thank you. So 1.9 meters per second, which also makes sense. All right. A toy gun shoots a 20-gram ball when a spring of spring decompresses. The amount of compression is 10 centimeters. With what speed does the ball exit the gun, assuming there is no friction between the ball and the gun? If instead there's a frictional force of 0.05 newtons opposing the motion of the, what will the exit speed be in this case? Do you want to give it a go? Do you want to have a go yourself and try to solve it and write the answer in the chat? If you don't, if you think you don't know how to do it, just let me know. Are you making progress? I'm gonna pick on you. Elastic potential energy. Well, there's no GPE. It's just kinetic. The only question is how fast we want to leave the nozzle. Yeah. So the question is how fast. Yeah. So we need the speed here at this moment. So at the start we have elastic potential energy, and at the end we have kinetic energy. There's no change in gravitational potential energy, so it's not going up or down. So we don't care about this. We're only interested in this moment in time. Any progress? What about you, Mark? Are you stuck? Are you finished? Good. Have you finished both questions or just Just the first one. Okay. So what answer did you get? Yeah, you got this. Did you get this part correct? All right, now you can cancel the 1/2. Divide by m. So v squared is k over m x squared. And then v is k over m v, which is square root of 12 over 0.02 times velocity, which is, oh, sorry, x times x times, which is 0.1. 0.1. And the answer is, okay. I hope you're not driving. When 2.45, 24 is a bit excessive. It's 2.45 meters per second. Mhm. And if you, if when there's friction, the elastic potential energy is equal to the kinetic energy plus the energy lost to friction. So the work done, which is kinetic energy plus work. Okay, so elastic potential energy, so it's 1/2 kx squared equals 1/2 mv squared plus, so that's question B, the work done, which is force times x, which is the distance traveled. X is 10 centimeters. Okay, so we can work out that v squared is 2, no, so that's kx squared over m minus 2fx over m. So square root, take the square root. And that works. Can you work it out, please? I figured, Mark. So what's the value? Can you calculate it, please? I'll wait for 1 more minute. Yeah, you've got an error. So it's 12 times 0.1 squared divided by 0.02 minus 2 times 0.05 times 0.1 divided by 0.02, and that should be 2.35 meters per second. It's slightly more. So if there's friction in the toy gun, then the speed will be smaller. Okay. All right. Yeah, that makes sense. Okay. The mass rolls over a 1 meter high table with a speed of 4 meters a second. With what speed does it strike the floor? How can we do that? So what do we have at A? No, let's not use suvat or projectile motion. No, let's make it simple. We're talking about energy. What do we have? What kind of energy do we have at A? Gravitational potential energy and kinetic energy. It's moving, right? It's moving at 4 meters a second, so it has gravitational and kinetic. And at B, it has kinetic only. So we can say that gravitational potential energy at A plus kinetic energy at A is equal to the kinetic energy at B. Because at here we have 2 types of energy and here only one. And there's no friction, so we're not losing anything on the way. So we have conservation of energy. So this is conservation of energy. Conservation of energy. Does that make sense? Do you understand? Mark? No. Okay. Drive safe. Okay, so mgha plus 1/2 mva squared equals 1/2 mvb squared. And all we need is to make vb the subject, 2 mgha plus mva squared equals mvb squared. We can cancel the m's, so the mass doesn't matter. So vb is equal to vb squared is equal to va squared plus 2gha. this looks awfully familiar. What does it look like? What does it remind you of? Some GCSE formula, no? You familiar with this formula? It's a Suvat equation. Yeah, it's one of the Suvat equations, and this looks awfully. They look awfully familiar, but they are. You got them from two completely different methods. One is conservation of energy, and one is just constant acceleration. And it's not a coincidence because you will have the exact same answer, of course. We did say that you could use Suvat and projectile motion, and you would get the same answer. Okay, so VB is equal to the square root of VA squared plus 2GH. A, of course, and that is square root of VB, so VA, so that's 4 squared minus 2 times 10 times 1. So it's 16, plus 16 plus 20, and that's 36, and that's 6 meters per second. So 6 meters per second, and here it's 4 meters a second, which makes perfect sense A as well. Okay, a power question. And a power is work divided by time, or it's energy divided by time. But then we recall that energy is force, well, work is force times distance. Work is force times distance. If we plug that into here, so power is force times distance divided by time. What is distance over time? Speed. So power is force times speed. You can use this formula as long as the force is constant and the speed is constant. Okay, a 0.5 kilogram battery operated train moves with a constant velocity of 0.3 meters a second along a level track. The power of the motor of the train is 2 watts, and the total force opposing the motion of the train is 5 newtons. Okay. So I have a toy train. Okay, traveling on a level track. They're not telling you the force with which the train pushes itself along the road. However, they do tell you that the force opposing the motion is 5 newtons. Can we work out the force pushing the train forward? Force of the engine. Okay, what is it? Nothing to do with GPE. This is to do with Newton's laws. What does this say? Well, yes, you can use F equals ma, but you don't have to. Depends on how you would use ma. Paracheater, yes, why? It is 5 newtons. It is the same as opposing force. How do we know that it is the same as the opposing force? Because it's a constant velocity, okay? Do you understand that? It's a constant velocity. That means the force of the engine has to be equal to the opposing force. Because otherwise it would be slowing down or speeding up, right? If this was 6, it would be speeding up. If it was 4, the train would be slowing down. But because they're balanced, that means they're constant velocity. So the power output is force times speed, which is 5 times 0.3, which is 1.5 watts. So efficiency, which is eta, the Greek letter eta, is the power out divided by power in. We know that the power in is 2 watts and the power out is 1.5 watts. So that's 0.75 or 75%. So the efficiency is 75%. So that means, yeah, 75% of the energy, the electrical energy goes into the movement and 25% goes into heat. So A, efficiency. B, assuming the efficiency and the opposing force stay the same, calculate the speed of the train as it climbs an incline of 10 degrees to the horizontal. Okay. So now we have an interesting situation. We have a train going up an incline. Going up an incline. 10 degrees. And well, it's gaining gravitational potential energy. So the power of the engine will go into power is the power that you need to move plus the power that you need to gain gravitational potential energy. If that makes sense. Okay, let's do it properly. The power of the engine will be used to overcome friction, power to overcome friction, plus the power to raise gravitational potential energy. So the power to raise gravitational is the rate at which the gravitational potential energy will increase. So assuming that it's moving with a speed v, the power to overcome friction is going to be force of friction times v, which is the velocity v, which we're looking for. The power to raise GPE is going to be mgh over time, because it's the rate at which gravitational potential energy is changing. So power of the engine is going to be Fv plus mgh over t. But h is L multiplied by sine 10. H is L multiplied by sine 10 degrees. So we can plug that in. So it's Fv plus mg L times sine 10 degrees divided by t. What is L over t? What is L over t? Speed, of course. So it's mgv sine 10. Okay, and from here, we can take v out of the brackets, v, f plus mg sine 10. And now v is equal to the power of the engine divided by f plus mg sine 10. And the power of the engine is 1.5 watts. It's the useful power, of course. And F is the force, which is 5 newtons, plus mg. Do we know? 0.5. So it's 5 times sine 10 degrees. Okay, so that will be 1.5 divided by 5, open bracket, 1 plus 10, 0.256 meters per second. It's going to be half the speed. Oh no, it's not half. Sorry, it was 0.3. Now it's 0.226. Okay, yeah, that makes sense. A little bit less than original. Does that make sense? Any questions? Yeah, force times velocity. I didn't mean to say velocity, but I mean, if it's force times velocity, force times. Just when you're talking about velocity, you can get into trouble because velocity is a vector and force is a vector. Then you have to talk about the scalar product. But generally, you can ignore that. Now, inequalities. Let's talk about inequalities a little bit. Inequalities is something that is kind of forgotten in the school syllabus, and it's a great pity that it is, because you only study very little inequalities in the course, and even at A level, it's very limited. So let's say we have something like this: x squared minus 4 is greater than 0. Do you know how to solve that? Parachita. So you're saying x is greater than 2 and x is greater than -2. Is that what you're saying? Or less than? Okay, yeah, that makes sense. So yes, you greater than 2 or less than -2. And in maths, we can use a special symbol like this, which means or. So you don't have to use the word or. That is true. -2. Another way of doing it is you can draw a graph. You can draw a graph, and this is a parabola. And we know that this parabola intersects the x-axis twice at -2 and at 2. And the question is, where is this parabola greater than 0? And greater than 0 means above, that the y is above the x-axis. So it is positive here. It is positive when x is greater than 2, because then, so where is the parabola? The question is, where is the graph above the x-axis? And it's greater than 2 or x is less than -2. Do you understand what I mean when I say graph is greater, graph is above the x-axis and graph is below the x-axis? So for which values of x, graph is above, and for which values of x, graph is below, sorry. Hello? Why is above x-axis is positive? Oh, because we say y is equal to x squared minus 4. And when we say x squared minus 4 is greater than 0, is the same as saying that y is greater than 0. And that means above the x-axis, because the x-axis is y equals 0. So if you can manage to draw a graph, you can solve an inequality straight away. So for example, let's take an inequality. Y equals x multiplied by x plus 1 multiplied by x minus 2 multiplied by x minus 3 greater than 0. Well, looks like all I need to do is to draw the graph. Y is equal to x plus 1, x minus 2, and x minus 3, was it? Yeah, x minus 3. And I can see the graph looks like this. So if I ask you now, can you solve this inequality? What's the answer? It's above the x-axis. So where, for which values of x is the graph above the x-axis? X is less than -1. From 0 to 2, and from 3, it's 3. But well done, Zeno. Yeah. So it's positive here, and that is x is less than -1. It is positive here between 0 and 2. X is 0 and 2. And it's positive here. X is greater than 3. All right, all three of you. Can you, how well do you understand it on a scale of 0 to 10? Okay. And if I say x plus 1, x minus 2, and x minus 3 is less than 0, you would immediately say, oh, well, x is between -1 and 0, or x is between 2 and 3. If only there was an easy way of drawing the graphs. And there is. There is. Look at these 4 dots. So this is what we call the method of intervals. So the function, the first thing we do is greater than 0. The first thing you ask yourself, when is it equal to 0? And it's equal to 0 when x is 0, when x is -1, when x is 2, and x is 3. And these points are known as the critical points. Critical points. The sign can only change in the critical points. Only sign only changes is at critical points. Between critical points, critical it is it is the same sign, Yeah, it crosses the x-axis. So if I give you this problem, so x plus 1, x minus 2, and x minus 3 is greater than 0. What you can do is say, first, identify critical points. By critical points. And put them on a straight line. So here's your straight line. And the critical points are -1, 0, 2, and 3. So these are the points where something happens. Okay. Now, what is 2? What is the sign? Is the sign when x is greater than 3? What you need to do is test any point from that interval. Let's say x is 10, right? Say x is 10. If you sub the x is 10 into this, do you get a positive number or a negative number? You don't need to calculate. You know that this expression will be positive. It's positive. So that means on this interval from 3 to plus infinity, because we've tested one value from that interval and it's going to be positive. Between 2 and 3, it's going to be negative. We can test that by subbing 1.5 into the expression, or we can just say, well, it changes sign. It's negative. Between 0 and 2 is going to be positive. Between -1 is going to be negative and positive. So you kind of draw the graph, but not really. You just say it's going to be positive here, negative here, positive here, negative here, positive here. Positive here, negative here. And that's it. And that means which ones do you need? You need the positive ones. 3, identify the suitable intervals. Positive or negative. You need the positive ones, so you dash them. And so the answer is x is less than -1, x is between 0 and 2, x is greater than 3. Super easy method, isn't it? So let's see if we can do the same. Same one. Let's say we have x minus 4, x plus 6, x minus 2, 2x minus 3, and x plus 3. And it's going to be less than 0. Okay. We find the critical points. The critical points. And it's going to be 4 minus 6, 2, 3 over 2, and minus 3. Okay, we put the critical points on a number line. So it's minus 6, and then minus 3, 1, 3 over 2, 2, 4. Now we test any point from one single interval. And suppose test an interval. So let's say x is 10 or 100. Why not? X is 100. So if x is 100, is this expression positive or negative? Positive, of course. So this is positive. Now between 2 and 4, all of them are positive except this one. So that makes the whole expression negative. Positive. Well, it can't be. Can't be positive and negative within the interval because in an interval it doesn't change. a function can only change sign if it crosses the axis. It becomes the point where it becomes positive or negative. It either crosses the axis or there's an asymptote. Well, I'll talk more about this. I'm simplifying a little bit. So here you have it's positive here, negative here, positive here, negative here, positive here, negative here. And we're interested in the negative intervals. So we need the negative intervals, and we can say that x is less than -6, or x is between -3 and 3 over 2, or x is between 2 and 4. There is a prettier way of writing this. We can say x belongs to from -infinity to -6, union from -3 to 3 over 2, union 2 to 4. That's the same thing as this. And let's draw that. Let's sketch that. Let's see if it actually works. Y is equal to x plus 6, x minus 4, x minus 3 over 2, x, what was it? Minus 4 plus 6 minus 2, 2x minus 3, and x plus 3. X plus 3, and that was 2x minus 3, 2x minus 3. And what did I miss? X minus 2? Yeah, x minus 2. Okay, so you can see that it is positive from 6, it's positive b from -6 to -3, from 1.5 to 2, and from 4. Now, the graph is not very accurate, but it serves its purpose. The purpose is to find the positive and negative intervals. How did you know that the interval between 2 and 4 was negative by plugging in a number from a different interval? Is it that intervals next to each other always have alternate positive and negative? Okay. Not always, but usually. Okay. It's intervals will alternate sign unless there's a special case, right? The signs will change unless there's a special case, and I will talk about the special cases next time. Okay, does that make sense? Yes, usually it alternates. The signs, let me write this down. Signs will alternate unless there is a special case. Well, actually, why not? Now, I just want to show you how we use it, how to actually use it, like, because not all inequalities look like this, right? Not all inequalities look like this. But let's say we have an inequality x squared minus 4x plus 3 greater than 0. Example. So we can factorize it. X minus 3, x minus 1 greater than 0. Critical points 1 and 3. We test a number, a large number, a big number. So let's say x is 100. 100 makes it positive. So positive, negative, positive, just like a parabola. Yeah, positive, positive, negative, positive. So we draw that. And we need the positive intervals. So x belongs from minus infinity, any number from minus infinity to 1, or from 3 to plus infinity. Voila. You see how easy it is to solve inequalities using that method. Or let me do another one. X cubed plus 6x squared minus 7 less than 0. Minus 7x, sorry. So you take x out, x, and you are left with x squared plus 6x minus 7 less than 0. You can factorize this, and you know how to factorize better than I do. X minus 1, x plus 7. What? Yeah, you clearly know how to oh yeah, okay. I actually haven't made a mistake. So there are 3 numbers, 3 critical points, 3 critical values, and the critical values are minus 7, 0, and 1. We test a big number, let's say from this interval. We test any number from this interval. Let's say it's 100. So 100 times 99 times 107, it's going to be a positive. So positive, negative, positive, negative. And voila. We need the negative intervals. So it's going to be this one and this one. So x belongs to from minus infinity to minus 7, or from 0 to 1. Does that make sense? Do you understand? Do you understand what I'm doing? Good. Let's. It also works. Funnily enough, it works if you have a fraction. It works for fractions as well. So, for example, x multiplied by x plus 1 multiplied by x minus 6 divided by x plus 2, x minus 3 is greater than 0. So you have a fraction. But I mean, multiplying by positive and dividing by positive, it doesn't matter, right? If you divide by negative, the sign changes. And if you multiply by negative, the sign changes as well. So you find the critical point. So 0, minus 1, 6, minus 2, 3. So minus 2, minus 1, 0, 3, 6. You test a very large number. Usually you test a large number. You don't have to, but it's advisable that you use a big number because it's easy to test. 100 times 101 times 94 divided by 98 divided by 102 divided by 97. They're all positive, so it's positive. Negative, positive, negative, positive, negative. It's going to be bam, 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 bam. Positive. We're interested in this interval, and this interval. So x belongs to from -2 to -1, from 0 to 3, and from 6 to +infinity. Possibilities are endless. So let's take a real life scenario. So a friend comes up to you and says, what is x divided by x plus 1 is less than 1 over x. So what do you do? Well, you just take everything to one side, make it 0. So x divided by x plus 1 minus 1 over x less than 0. You find the common denominator, so it's going to be x. There's going to be x plus 1. So it's going to be x squared minus x minus 1 divided by x plus 1 less than 0. And you need to factorize this. Can you actually factorize it? I'm having doubts. I'm a bit lazy today, so I'm just gonna use my friend calculator. And oh yeah, it can factorize it. Okay, the factorization is horrible-ish. So it's going to be x minus 1 minus root 5 over 2. And x, okay, I'm sorry for that, but it's just, should have used better values. Yeah, but x minus 1 plus root 5 over 2. X plus 1 less than 0. So you find the critical values. So this is 1 minus root 5 over 2. So what's that? 1 minus root 5 over 2. So that's minus. So it's going to be minus 1. 1 minus root 5 over 2. And it's going to be 0. And it's going to be 1 plus root 5 over 2. So we test a big positive value again. Plus, minus, plus, minus, plus. And you need the negative ones. So the answer, x belongs to from -1 to 1 minus root 5 over 2, or from 0 to 1 plus root 5 over 2. So you could solve an inequality like this, which looks absolutely horrendous. Okay, the factorization is not nice, but you understand the logic here, right? You only need to factorize it, and once you factorize it, it's done. You just draw it and bam, 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 finished. Okay, there are a couple of nuances which I will talk about next week. First of all, if there's a power, it's a different situation, and if it's less than or equal to. So there's two more nuances at least that I need to talk to you about, but otherwise it's a really beautiful method. It's called the method of intervals, and it's in the assignment. So yay, exciting. So I'll see you next week. All right. Enjoy.
Thank you.
Welcome.